In this video, we're going to do a brief introduction to a key concept called entropy. Now, entropy is a measure of disorder, so how disorganized a substance is. In a nutshell, according to the second law of thermodynamics, which is a pretty key physics and chemistry principle, or law, I should say, the universe tends towards disorder. So particles are, I hate to personalize them, but are trying to get into a more disordered state that would generally be spontaneous, so happen on its own. So what makes things become more disordered? So an increase in entropy means things are becoming less organized. The first of these factors is temperature. If I imagine this to be a pure substance in its solid form, and these are vibrating in 3 dimensions, and I add more heat energy, so I increase its temperature, they're going to vibrate enough to expand, but not yet melt. I don't want to get that far yet. But what it means is this one could be vibrating this way at the same time as this one could be vibrating that way. So there's different ways I could show that vibration at any moment in time. They're still averaging out to be about the same distance apart, but it is not as well ordered as when they're much closer together. So when I heat a substance, and in this case I'm using a solid, but it could be a liquid or a gas, the particles have got more energy to move, so they're less likely to be organized. They're more likely to move around randomly. The second of these is taking that temperature increase a step further. When I get to the point of melting, so it's expanded out enough now that I can start breaking bonds and these can start flowing. Of course, they're going from vibration to flowing. Flowing is much, much less organized, much more disorganized or disordered than vibrating a lot in a solid. So when we go from solid to liquid, there's clearly an increase in entropy because the particles can actually flow past each other. This one doesn't have to stay over here, it could end up over here because it can flow. Same thing with a gas. It's a fluid, so the particles can flow, so it has even more disorder, a higher entropy than the liquid phase or state of matter. This state of matter one sort of trumps everything else. If you see something with solids on one side of the equation, then that, and not on the other side of the equation, then that's a pretty sure sign that the side with the solid has got a lower entropy than the other side of the equation. The last of these is particle type. So if I reorganize my particles a little bit, and then what I do is I have another one over here, another substance over here. I'm sorry, I'm going to go over my things. You could argue that these have got the same level of disorder. And they would. They're meant to be the same distance apart, sorry, just not quite perfect. Okay, so you could argue that the blue and the red have got the same level of entropy. Let's say, for argument's sake, that they are liquids and I allowed them to mix. They could start getting involved with each other and increase the level of disorder. There are many different ways I could organise these 8 molecules so that they are arranged a different way in space at any time, and that would mean that there is a high level of disorder. So if you've got lots of different types of particles in a substance, then that also increases the disorder. I could increase the disorder dramatically, not just a little bit, by replacing one with another type of particle like that. That increases my different possibilities for how to arrange the molecules or ions or whatever they are considerably. So doing things like dissolving in a solvent really dramatically increases entropy as well, because there are more possible ways the particles could be arranged, and that all those permutations or possibilities increase our entropy, so give us a positive delta S value. And as I say, this is what the second law of thermodynamics is basically saying, that this would be more stable because it has got more disorder.